In this video, we're going to explore reactions at the benzylic position. Recall that the benzylic position is that which is one away from a benzene ring. Straight from the textbook, section 21.5, we see that that position is special in that we can generate a cation there fairly easily, an anion there fairly easily, or a radical there very easily. Why is it so easy to generate these species? Well, because each one of them is resonance stabilized. As we push the arrows around for resonance, you'll notice that the position of the cation can be ortho. Little preview for chapter 22. Ortho is a position that is one away from a group already on the benzene. This should be review to most of you. Further resonance generates a para cation, where the cation is as far away from the group as possible, and the final resonance structure, where the cation seems to have disappeared, is another ortho position cation, with the cation on a carbon, one away from the group that's already on the benzene. Resonating further, you see that this resonance form is just the benzene resonance form of the original benzylic cation. Similar stories exist for the stabilization of the benzylic anion, giving ortho, para, and ortho anions, and benzylic radicals, giving ortho, para, and ortho radicals in the resonance forms. A new reaction that you haven't seen before is the benzylic oxidation of aromatic species. For this to occur, you need a few things. You need a benzylic carbon that has at least one hydrogen. You need some method of forming chromic acid. This combination generates chromic acid, as does this. This is not new to you. And a further stipulation which you haven't seen with chromic acid before is you need quite a bit of heat for this reaction to occur. This is important because if you want to avoid one of these reactions and oxidize something else in the molecule, you can do so by simply not having heat present. With the presence of heat, any benzylic position that has hydrogens becomes a carboxylic acid. Similar story here, where this carbon and this carbon have two H's that are benzylic. They will both oxidize to a carboxylic acid. If you're curious what happened to the other two carbons, I'm only going to show it this one time. They also get oxidized, but this is not a useful way to create this oxalic acid over here. There are many other more facile ways to do so. Facile, some people say facile. This position here is benzylic, but there are no hydrogens there, so no reaction happens at this position. Whereas a CH3 will oxidize to a carboxylic acid, as will a CH2. There would be a side product of formic acid here, where this final carbon ends up being formic acid. No reaction at this benzylic position. There's no hydrogens. This carbon becomes a carboxylic acid. These both become formic acid, but those are side products. Something I didn't mention, benzylic acid oxidation takes advantage of carbocation stability at the benzylic position. I think you can see, even though we're not responsible for the mechanism, that if you can generate this cation, then OH would attack from the water present under these conditions, and you get an alcohol. It's the alcohol that gets oxidized to a carboxylic acid. A review reaction from chapter 8 was the use of NBS to create an allylic bromide. This takes advantage of the final set of resonance structures here. It's a radical mechanism, so benzylic radicals are easy to form, as are allylic radicals, which we learned about in Chapter 8. And the allylic radical will form an allylic bromide. What will happen to our benzylic position here? Under the same conditions, we will generate a benzylic bromide here. And this is a useful synthetic outcome. Before we move on, a reminder, we're supposed to know what benzylic means. That's a position 1 off of a benzene, as allylic is a position 1 off of this group here. There, that group. Compared to allylic, it has the extra carbon, just like this group is similar to this, except it has the extra carbon when it's benzylic. I believe a benzylic without the extra carbon is just called phenyl, and a allylic without the extra carbon is called vinyl. Our final discussion on benzylic reactions is called hydrogenolysis. It only works properly with benzylic ethers. Hydrogen will perform what's called a homolysis of this sigma bond, placing an H on each side. If you put an H on the left side, this is really now a methyl group attached to benzene. That's phenyl CH3. That's also known as toluene. And this portion also gets an H on the O. That is now an alcohol. So the original molecule can be thought of as a protected alcohol. So why is this reaction useful? Well, it can prevent other reactions of R. Ones that an alcohol would react, that we don't want to react. We can simply protect the alcohol first as a benzylic ether, which I will show, and then do your chemistry, and then deprotect using hydrogen and platinum in a reaction called hydrogenolysis. Hydrogen being used to split a molecule apart. Using a benzylic protecting group could be illustrated here. I want to do a synthesis of a terminal alkyne into an internal alkyne, which we explored in Chapter 7. To do so, we need to deprotonate a terminal alkyne and then add a carbon with a leaving group to do an SN2 reaction. It is impossible to deprotonate a terminal alkyne without first deprotonating an alcohol. We're talking about a pKa of 17 for the alcohol and a pKa of 25. 17 always reacts before 25. So we need to mask our alcohol as something where there is no proton on the O. I suggest a benzylic ether. How do I make a benzylic ether? Let's use a Williamson ether synthesis. So first I want to take my starting material and convert it to the benzylic ether. First I need to deprotonate the OH using a strong base. KH would do the job. Now I'm going to have an alkoxide nucleophile. I just need a benzylic carbon with a leaving group, similar to this right over here, with a bromine on it. And that would just be benzyl bromide, wouldn't it? And now you've got a protected alcohol that can be deprotonated at the terminal alkyne position, and then a synthesis can be performed, and after that hydrogenolysis will reveal our target molecule right here. Deprotonation using a similar base, it's strong enough to also deprotonate a terminal alkyne, will yield an anion on this carbon right here, which is a nucleophile. Backside attack on an ethyl with a leaving group in an SN2 reaction accomplishes our synthetic goal of adding an ethyl group to the terminal alkyne. H2 and PT, if done under the right conditions, we can avoid reducing the alkyne while reducing or doing hydrogenolysis of the benzylic ether. I hope you found this video about reactions at the benzylic position useful, and I look forward to the next video.